This time we're looking at Secureum race number 8, and this one is also about NFTs, just like the last ones, but this time we're not extending an existing NFT implementation like the OpenZeppelin implementation, but rather we are adapting from such an implementation directly. So we basically just copied the code of some implementation like OpenZeppelin implementation and adjusted it to include a few bugs, I guess. And well, it contains all the things that we would expect it to have, like transfer events, approval events, owner of, balance of functions, approve functions, transfer functions, minting functions, burn functions. It also has this safe mint feature where it basically calls the on ERC-721 received function, the callback, and expects it to return this function's selector, so the 4-byte hash, or the 4 bytes of the function selector's hash should be returned here, so which is very unlikely to happen at random when you call some contract where you're not sure whether it supports this standard and you call this function and it returns exactly this selector, then you can be quite certain that this isn't just by accident, but that this actually means that the code wants to tell you that it supports this ERC standard. And to make this really easy to implement for receivers, it also provides this abstract contract, ERC-721 token receiver, which it can simply extend. So a receiver can simply extend this receiver abstract contract. Abstract means that this contract is not supposed to be initialized and deployed on its own, but rather that it is a contract that does contain code, but it is more close to an interface in the sense that you're not supposed to deploy an abstract contract basically. And all it does is it has this on ERC-721 received callback function, and it simply returns this function's own selector, as you would expect. So let's take a look at question 1, which says that the security concerns addressed explicitly in _mint include. So this time this is about the security concerns that are already addressed in the _mint function. So this is a bit different than usual, where we actually have to look which of these are still present and not addressed in the function. It says here that A is preventing minting to 0 address, preventing reminting of NFTs, so basically of already existing NFTs. Then C, transparency by emitting event or none of the above. So let's take a look at the _mint function. We have it right here, and it takes 2 arguments. It takes the to address to where this NFT should be minted to, and an ID, so which NFT should be minted, and it is internal. And usually this function is then called by some public mint function that does some sort of authentication or expects some sort of payment for the minting. And usually also the ID that is passed in here is incremental, so the same ID never happens to be passed in twice. And yeah, the code itself, it basically checks, it requires the to address to be unequal to the 0 address. So we have a 0 address check here, just as the first option of this question demanded. Then we have a require statement that requires the current owner of this ID to be equal to the 0 address. So since we are minting a non-existent NFT, it shouldn't belong to anyone yet. And this prevents reminting already existing NFTs. Now the question is, how do you handle burning here? Because if you burn by setting the 0 address, that would theoretically mean that you could remint the same NFT again after it has been burned, simply by passing the same ID in here again. But usually that's just not possible, because the only function allowing to access _mint does passes an ID in incrementally, and there's just no way to pass in a previous ID once again. But this is actually something to think about, when the ID is actually not incremental, but can actually be specified or something like that. Then the project owners might not actually want things like that to happen, like want to allow burn NFTs to be reminted But that would theoretically be possible when this information has been deleted with a burn, basically. But it doesn't really matter here. All that matters is that we check against the zero address, we make sure that we can't remint. And the last point was that there should be an event emitted for transparency, and we indeed have a transfer event that is being emitted here. It comes from the zero address because it comes from nowhere, so that sounds good. It goes to the to address, and it also specifies the ID that has been minted, and this matches with the declaration of this transfer event, which is also indexed from, indexed to, and then the indexed ID that should be passed. So the order of these parameters seems also correct. So all in all, these security concerns seem to be correctly addressed, all of them, for question 1. Then we have question 2, which says that there are security concerns in the underscore burn function. So this time it's not about security concerns that have already been addressed, but this time it is actually about security concerns that are still there. So it says that A, anyone can arbitrarily burn NFTs. B, potential integer underflow because of unchecked. C, incorrect emission of event. So let's take a look at underscore burned, or burn. The underscore burn function, we have it right here. And this time, for some reason, this underscore burn function is external, even though the underscore at the beginning of the function name would imply that it is a internal or private function. This time it is actually marked as external, which indeed means that anyone could arbitrarily burn anyone else's, well, NFT. That doesn't sound good. And then the question was also asking about an underflow that could happen within an unchecked block, and we indeed have an unchecked block where a subtraction is happening. So that could indeed, in theory, happen, but for that, this subtraction would need to be run multiple times, basically, and this is prevented because you can't simply, burn IDs that don't actually exist. There actually needs to be an owner. This NFT that is being burned actually needs to be owned by someone, and then it subtracts 1 from that owner. And if someone owns at least one NFT, this one NFT will also have a balance of 1 then, basically. But this not causing an underflow relies on the other functions correctly increasing and decreasing balance of 2. So minting should always increase it by 1, and transferring should increase it for the receiver but decrease it for the sender, and so on. But that on its own, it does not have any chance to underflow because it correctly checks that only NFTs that are actually owned by someone are subtracted from that owner. So then the last option was about the transfer event, yes. So this time, we already talked about the transfer event, which was transfer from, to, and then the ID, and we can see that it is being, transferred, burned from the owner to nowhere, so to the zero address with the specified ID, and that is the correct usage of this event, and therefore it's just fine as it is. So we can say that yes, there is indeed a real issue. This isn't just a concern, I would say, but this is actually a real issue that anyone can arbitrarily burn NFTs. Potential integer underflows because of unchecked. Not really, this can't really happen, assuming the rest of the contract code is correct and the check is working correctly. This cannot happen here. Then C, we have an incorrect emission of an event. This is also not the case. It seems to be emitting the transfer event just fine. So that's it for question 2. Moving on to question number 3, which says that the security concerns already addressed explicitly in the underscore SafeMint function include A, validating if the recipient is an EOA, B, ensuring that the recipient can only be an EOA, C, validating if the recipient is an ERC721 aware contract. So if we look for the underscore SafeMint function, we can see there's actually 2 of them, with the only difference being that one of them has a data parameter where you can pass some bytes, some memory bytes to it, and this is then passed onto the callback, whereas in the other case where it doesn't have a data parameter, it just passes an empty bytes to it basically. So otherwise these two are completely identical, so we can just look at one of them. And first it calls the underscore min function that we already looked at. Then it requires that either the code length is 0, which means that the receiver, the 2, is an EOA account, so therefore no further checks have to be made. But if it is not an EOA account, then it calls the on ERC2721 received function and expects this callback function to return the selector. But nowhere here it actually requires the receiver to be an EOA account. It can be either, and if it is a contract, then it makes sure that this contract is ERC721 aware, but otherwise it is fine if it is either contract or EOA. So for question 3, we can say that it does indeed validate if the recipient is an EOA to then decide whether it should validate if the recipient is ERC721 aware, but it is not ensuring that the recipient can only be an EOA. So that's question 3. Next we have question 4, which is all about the approve function. It says that the approve function allows the NFT owner to approve a spender. It allows the NFT spender to approve an operator. It allows the NFT operator to approve a spender. So you might be wondering what an operator is. So let's talk about how approvals are different to ERC20 in NFTs. So in ERC20 we gave an approval, or we call the approve function to give some spender an allowance over the ERC20 tokens that we own. And we often, it is not really a good thing, but often for convenience, protocols are just given infinite approvals, which means that you only have to approve all of your tokens of this type once to the project, and then they can just make use of all your tokens, of all your USDC or whatever. And in NFT it's a little bit different, because the approve function in NFTs, it only allows, well, giving approval for a specific ID for one NFT at a time. And that is a little bit inconvenient because, well, you have to make a lot of approve calls if you own a lot of NFTs that belong to this contract, basically. And as an alternative to what is basically unlimited approvals, we have operators in ERC721. And operators basically get something like an unlimited approval to all of the NFTs of this contract, of this collection that you own. So an operator is similar, has then similar rights to you as an owner, but this operator can then also make calls to the approve function to basically approve two new spenders, similar like to how the owner can do. So to summarize, the approve function allows the NFT owner to approve a spender. Yes, the owner can approve a spender. The spender cannot approve an operator. That would be strange. But the operator, who is more powerful than the spender, the operator can approve a spender. That is C. We can see that in the approve function, which is right here. So this is the approve function. The approve function takes as arguments the address of the spender and the ID of the NFT that we want to give an approval for. And it then checks who owns this NFT ID. And it then makes sure that either the current caller of the approve function should be this owner, or there should be a operator declared is approved for all. So being approved for all is equivalent to being an operator of another person. So it checks whether this owner has declared the current message sender to be an operator who is approved to make use of all these NFT tokens, and only if one of these two things is true, then the approval to the spender is given for this specified NFT. So, and that is how approvals basically work in NFTs, and why only A and C are the correct options here. So that's question 4. Question 5 is very similar to question 4, also being about approvals, but this time about set approval for all. So this is about setting, declaring an operator. So is this function A about approving the message sender to manage operators NFTs? So that doesn't make sense because the operator is approved to manage the message sender's NFTs, so A can't be right. B, it gives everyone approval to manage message sender's NFTs. You certainly don't want everyone on the planet to have approval to manage my NFTs, so that doesn't sound right either. Then C, it revokes everyone's approvals to manage message senders NFTs. Well, if you just look at the function name set approval for all, it doesn't sound like revoke approval for all, so that also doesn't sound right. So none of the above seems to be the only correct answer. But let's actually take a quick look at set approval for all, at the actual function, and we can see that it is a very short function which basically takes in, again, two parameters. One, the address of the operator, then a boolean whether the operator is approved or not. So we can set this to revoke access but also to give access, and it just sets this mapping that we've already encountered in the approval function here above. It sets in this mapping for the current message sender, so for the owner, set the following operator to be either approved or not approved, and then emit an appropriate event to communicate this change or to lock this change in the blockchain basically. So none of these options actually make sense for question 5. Next we have question 6, which is about the security concerns in the transfer from function, which include A, allowing the message sender to transfer any NFT. That sounds like a real issue, not just a concern. B, NFTs are potentially stuck or get potentially stuck in recipient contracts. Well, we already know this will be true simply because this isn't the safe transfer from function. So this one isn't the function that actually checks the callback, is ERC-721 receiver callback. So we already know that yes, NFTs will be potentially stuck in the recipient contracts, but that's the purpose of transfer from. It's there for backwards compatibility reasons, and it doesn't make this check on purpose, but it is still a potential concern, I guess. And C, there are potential integer underflows. So let's take a look at the transfer from function. So here we have safe transfer from, which calls the normal transfer from function, and it requires, as we expected, that if the receiver is a contract, then the ERC-721 received function callback is called, and it should return the expected selector. So that is just like we thought it should be. And this check is not happening in the normal transfer from function, which is right here. And therefore, indeed, if the to address is a contract and it doesn't support NFTs, then they can get stuck there. So next was whether the message sender can just transfer anyone's NFTs. So the first check, just make sure that we don't transfer anything to the 0 address. The second check, make sure that either the current message sender is equal to from, so the person calling this function is also the from, which kind of implies ownership, I guess. So that sounds like a good check to have. Or is approved for all from message sender, so meaning that or the current message sender needs to be an operator for the currently specified from address. And then finally, or the get approved, so the NFT ID should be approved for this message sender as a spender. So all of these things sound correct, like they're correctly checking that nobody can just transfer anyone's NFTs. But there is a problem here, which is that the actual owner of the NFT isn't checked at all. So we can just specify someone else's ID here, and then we can just specify ourselves, so our own address as the from, and call with our own address. That means that this first require statement will pass, but this ID doesn't even belong to us. But still, this just passes these two requirements. then the balance of from, so our balance is decreased by 1, and then again increased by 1. So it goes from 0 to -1. Well, kind of. It wraps back and then wraps forward again, and then we officially have a balance of 0, but we are now owner of this NFT according to this set here. And it also deletes the previous approval that was given and emits a transfer in the end. So we can indeed just just transfer anyone else's NFTs, because this check is not complete. It makes sense, but it is actually not doing the most important check, which is checking that this ID even belongs to the specified from address. And this also means that we can make transfers from addresses that don't even have any NFTs, which means that this can decrease. So if we had specified ourselves as from, but some other address as to, then we would get a negative balance and the new address would get a 1, as it should be, correct? But we would end up with by wrapping around, we would end up with an underflow. So for question 6, it indeed allows anyone to send any NFT basically. And see, there's also, because of this, there's also a potential integer underflow. Then we have question 7, which asks, which of the following are true? A, NFT ownership is tracked by _owner of. And we already know this to be true because this is a mapping that we've already seen. It goes from number, from integer to address. So we specify the number of the NFT, the ID of the NFT here, and in return we get an address of the current owner. So indeed it tracks ownership. Then we have B, NFT balance is tracked by _balance of. Similar here, this time it is a mapping from address to integer. We give it the address that we want to check the balance of, and we get in return an integer number that says how many NFTs does this address have. Assuming we are going to fix the transfer from function, this also tracks this correctly, but yes, that's its purpose. Then we have C, NFT approvals are tracked by getApproved. So getApproved first sounds like a function name, but this is actually also a mapping. You can see it right here. It's a mapping from uint, the NFT ID, to address, to basically the spender. So this is a mapping that stores who is the approved spender for the specified NFT ID. And the reason why this is not with like underscore and approved to or something like that, similar to the other mappings, is that this one is a public mapping, which means that it automatically gets a public function from Solidity where you can just call getApproved, pass it an NFT ID, and it returns the address, the approved address for this NFT ID. And that's why the name is quite a bit different to the other ones, but it is indeed a mapping that tracks approvals. So C is also correct. Then we have D, NFT operator can transfer all of owner's NFTs. And that is also true because that's the whole purpose of an operator. An operator has the power to transfer all of the NFTs of this contract in this contract of the owner, and can also give approvals to spenders for these NFTs. So A, B, C, and D are all correct for question 7. And finally, we have question 8, which is quite easy now that we have already understood all of the other questions. It asks, which roles does ERC 721 recognize? An owner role, a spender role, so approved addresses, and operators which are approved to use all of the NFTs. So all of these can be considered roles within a ERC 721 NFT contract. Yep, and that is race number 8.